Hello and welcome. So here's a simplified view of what a traditional compiler pipeline might look like. You shove some source text down one end, and on the other end comes assembly. And in between you do some parsing, some type checking, and you might update some piece of state. But nowadays we expect rich tooling for our languages. We want editor integrations that show errors on the fly in real time as you type. We want to be able to jump to definition and get the type of the expression at our cursor. So the tooling must be able to answer many different kinds of questions, not just spit out assembly. Another thing that we want is incremental compilation. This is especially important for real-time editor tooling in big projects. But how do we achieve this? In this talk I'm going to show one way to do it. My name is Olle Fredriksson. I'm into programming languages and compilers, and I used to be an academic working in programming languages, but now I'm in industry. I'm at a startup in Norway called Folk, writing web apps in Haskell. So my work isn't always related to programming languages, although I sneak some compiler stuff into my day job from time to time. So in this talk I'll show one way to solve these problems, which is to construct the compiler around a build system library called Rock, which is highly inspired by the paper here, Build Systems a la carte. And it's also quite similar to the Rust library, Salsa. So if you're using Rust, you might want to check that out. I'll both show how a query-based compiler is structured and how Rock works internally. I'll also explain how to solve some of the problems that you'll run into if you try this at home. Rock was built for Sixten, which is a dependently typed functional programming language with unboxed data. And the reason for writing a new build system library is that existing ones are file focused, and in a compiler you mostly want to work with data in memory. Also, since this is something I do for fun in my free time, I can shave as many yaks as I want. Alright, so just to whet your appetite a bit, here's where Sixten is right now. I'll show some code. So here's an editor with some Sixten code in it, and it's running the Sixten tooling built around Rock. And in this module we're defining a data type of trees, which can be a leaf or a branch, and then we define a map function over those trees. And I just want to show that the editor integration works in real time. So you can see when I hover over things, it sort of highlights all the occurrences of them, and it'll show errors in real time. So here it inferred an int, but it expected a tree there. What else can we do? We can jump to definition. We can rename things. We can do completion. And this is actually type-based completion. So it'll show you suggestions that fit with the type that's expected. Right, so that's some of the stuff that Sixten can do. Back to the presentation. But how do we actually write these kind of compilers? It might be a good idea to take a step back and think of how it's going to work. So I assume many of you have seen makefiles before. So think of a really well-written makefile. Make allows specifying many different targets, that is queries that you can make, and they can depend on each other. So for instance, here target 3 depends on 1 and 2. So you could imagine a makefile with different targets for the different actions that can be performed in the editor tooling. Make is also able to do incremental updates by using timestamps and only recompiling if there are dependencies that have changed since the result of the current target was updated. We won't use timestamps, by the way, but that's not the point. All right. Okay, so how to write a compiler in this style. And I find a good way to start is to write just a single query fully from scratch. So we don't know anything, and now we want to write a query, in this example, to get the type of a qualified name. That is a name that also contains the module that it comes from. So to get the type of a name from scratch, we first have to, at least in Sixten, get the file name of the module, and that's something we do with this module file name function. And when we have the file name, we can read the file from disk, and once we have the source code read into memory, we parse it to get the parsed module, and then we do some name resolution to see where what the different names in the source code refer to. And finally, when we have a resolved module, we can look up the name among the definitions in the resolved module and infer the type of that name. And in the process of inferring the type of the definition, we might encounter other names that we need to get the type of, and then we can recursively call this fetch type function. So an example usage here is to get the type of the map function from the data list module. So the next step is to split this big function into smaller functions. So now we make a function to just get the parsed module from a module name, and there we just get the file name and read the file and parse it. We make a function to get our resolved module with names resolved, and in that function we call the function to get the parsed module, and then we resolve the names. And then finally we rewrite the fetch type function again to use this fetch resolved module function, look up the definition and infer its type. So notice here that each of these functions are doing a longer and longer prefix of the longest task, and that's a pattern that I've found you often see in these kind of compilers. Okay, so now we'd like to centralize the fetching of the different entities. So we want to create a type for the different keys or different targets that we can get or fetch. Now a problem is how to write a general fetch function that, given a key, gives us its result. Because the different keys, we expect to return different things. When we fetch a parsed module key, we want to get the parsed module, and when we get a resolved module, we want to get a resolved module, which are different things. So given the current key type, we can't give a good type to this fetch function. So we turn to generalized algebraic data types, or GADTs. So here we define the key type as a parameterized type where the parameter signals the return type that a query should have. And GADTs, they allow each constructor to return a different type for the parameter of key. We should really call it an index and not a parameter. So the trick now is to make the different key constructors use the index to signal the return type that we should have for each query. And now we can give a good type to fetch by making the return type agree with the parameter to the key. This isn't a new idea. For instance, Haxel, which is a Facebook library, does something similar with its sources and caches. And this way of using typed keys is also mentioned in the journal version of the Build Systems a la carte paper. Okay, so we've seen the start of an example of how to structure a query-based compiler. We're not done yet. We'll continue looking at the example, but now we'll at the same time dive into how ROC works internally. The most important type in ROC is the task type, and it's a monad. And if you know Haskell lingo, it's basically a reader of a fetch function on top of I/O. What this means is that a task can chug along and do some input and output, and when it needs the result of some query, it can fetch it by using this function that it's given, which is a kind of fetch function that can fetch any key. So the key here is that a task computation is parameterized by what happens when you fetch. And then we can implement the real fetch function that we can use when we implement tasks like this. So it takes a key, and then the task grabs a hold of the fetch function from its environment and calls it with that key. Another core type is rules, which associates a task with each key. And rules is the type that you need to implement to define your compiler's build system, that is, its makefile. And given a set of rules and a task, so a set of rules and a task, that task can be run by calling the rules function anytime a key is fetched in the task recursively. And that looks like this. So here's a summary. We have a task monad, which can fetch. We have the rules of the build system, which maps keys to tasks. And we have a way to run tasks given a set of rules. So now we'll rewrite our running example as a set of rules instead, using the key type that we defined. So here we're doing the same thing as when we had split our big function into 3 functions, but here we're first doing a case split, that is a switch on the key that we're given and acting accordingly in each case. So for instance, when the key is the parsed module key of some module name, we do as before, get the file name for that module, read the file, parse the module. Within the same run of the compiler, we often make the same query several times. For instance, in this example, we're getting the type of 2 functions from the same module, the map function from data list and the folder function from data list. And both of these depend on getting the resolved module for the data list module and the parsed module. So getting the type of these 2 functions shares a big part of the query graph, and it would be very wasteful to compute the queries from scratch each time that happens. Instead, we want to make sure that we cache the result after we've done it the first time and then reuse it. So if we've gotten the resolved module for data list during getting the type of data list map, first, and then we get it again during computing folder, then we will just reuse the cached result. And that's implemented using this Memoize function. So Memoize takes a mutable reference to a dependent hash map, so basically a table that maps keys to their values, and it makes sure that in its input rules, it gives you a new. It takes a rule system and gives you a new rule system where each of the queries is performed at most 1 in each run of the compiler. And then we can make a new run function that, given a task, performs it by layering this memoization function on top of our rules and then running the task. So that's the run memoize task function. So memoization reuses cached results from the same run of the compiler, and therefore we have the guarantee that the result will be the same because we within the same run of the compiler we assume that all the inputs stay the same. But for incremental updates, we'd like to use the results from a previous run of the compiler, and then we don't have the guarantee that all the inputs are the same. Some of them might have changed, and what we do then is called verifying dependencies. So returning to this query graph and assuming that we have run all of these queries once and then made some changes to some module, and then we run the queries again. How do we know if we can reuse the old results? Well, we have to check. So for each query we keep track of their dependencies and the values. So for each query we track all the fetches they do and what the value of that is. And to check if we can reuse the value of a query from the previous run, we recursively compute all the stored dependencies from the last run for that query, and if all of them are the same, we can reuse the old value without doing any computation for the current query. The code looks like this. I won't go into detail, but one thing to note is that we have to mark our queries with whether they are an input or a non-input, so whether they can change even though their dependencies haven't changed. So a new rule system needs to say that getting the parsed module is an input because we read a file from disk, but the other queries are non-inputs because they only depend on other queries to get the result. And to run this kind of task with dependency validation, we can just layer this onto our rules. So we have our original rule system, and then we verify the traces. In this case, we just check the hash of the value instead of the value itself, and on top of that we do memoization. So we can pick and choose what we want to do when a query is performed using ROC. Another important caching strategy for tooling is reverse dependency tracking, and I'll show an example here. So let's say we're working in a project with 3 independent modules: data list, map, and set. And now we make a change to the data map module and fetch something from another module, data set, for instance, to get the type of a definition there. This will trigger dependency validation of all the dependencies in data set, even though that module hasn't changed. And reverse dependency tracking is a way to fix this. It lets us keep the memoized results for keys that we know haven't changed. Instead, we start from what we know has changed, the data map module in this case, and recursively invalidate all keys that depend on it. So we invalidate everything in data map because that has changed. But if we make a query in data set, that can just be reused from the memoization cache. So this way we'll avoid a lot of work in our real-time tooling, where we often have a file watcher that can tell us what modules have been changed since the last run. Okay, so now we know a bit about both how to write a query-based compiler and how ROC works internally. Now I'd like to talk about how to solve some of the problems that you'll run into. So one is parallelism. I tried for a while to have automatic parallelization of applicative actions, basically actions that are run in a context where the library can see that there are independent parts. It would fire them off in parallel. but I could never get more than about 10% speed up from that. And that's also done in that Haxel library, by the way. And I think the problem was that the queries in a typical compiler are just too granular, whereas Haxel queries are typically heavier. So I scrapped that and just do manual parallelization. And the way I do that is just, instead of mapping this type checking function over all the input files, I do a pooled map concurrently, which is a map function that runs in parallel up to some limit, so up to the number of cores that you have. And just doing this gives a nice speed up on my machine. And it's actually really easy, because any queries can be computed in any order. And with memoization, anytime you perform the same query twice, the second time will either directly get a cached copy, or it will wait until it's done. Just imagine doing something like this in a traditional compiler that updates state internally. Here we just let Rock handle the state for us, and since Rock is written in a thread-safe way, it just works. Another thing that you'll often want to do in a compiler is to track source locations. And this is to be able to show where errors, type errors for instance, show up in the source code, in your error messages. So what I do is I add another constructor to my syntax tree for terms or expressions. That is a term that's annotated with a source location. And just doing that, the annotations will look something like this. So here's a module with 3 definitions, f, g, and h, and we have annotations on every sub-expression saying what line they're on. There's a problem with this though. So look at what happens if we add a line here to G. I'll go back. So we add a line 10 to G. Then all the lines of H are pushed. So they started at 11 and went through 14, and now they're at 12 to 15. And the problem with this is that this will invalidate the cache that we have in Rock. So even though age hasn't really changed, we'll have to redo all the queries that have to do with age. And what can we do about this? Well, we use relative source locations. So for each definition, we do store the absolute position, but just once and sort of on the side. And then in the AST, we only store positions relative to that absolute position. And that means that even though we added a line here to G, the syntax tree of H hasn't changed, so we can reuse old results for that. Another thing that we'll want to do is to track errors. And it would be quite annoying to have a bunch of queries that return errors, and when you fetch that query, you have to handle the error. Instead, it's nicer if the queries can return errors, but you don't have to handle the errors when you fetch something. And that's something that this Rock library supports. Basically, anytime there are errors, you return them on the side, but fetches, they don't return those errors. And the errors that are returned on the side, they're put into some map or something, a dictionary, and shown to the user. And to make the compiler still work, you have to have some way of returning something even in the face of errors. So what I do in Sixten is I return some Sentinel AST node when there are failures. Okay, so I think query-based compilers are a very promising way to write compilers. After you get the hang of how they work, they're very liberating to write, because the library takes care of incrementality once and for all. And they make tooling a joy to build, because you're free to make queries for anything at any time, which also means that they're easy to parallelize. Thanks for watching, and thanks for inviting me to give this talk. It's been a pleasure. Bye.
Thank you, Ole. Just for the benefit of the people who might not have seen the question in the Q&A panel. So I'm going to read it so you can answer it also live. So there was a question whether the approach does improve incrementality indeed, but whether or not it comes at the cost of increased memory, because the compiler can't throw away the previous stages of the compilation.
Yeah, that's absolutely correct. So because you're putting everything in a memoization cache, and you're never taking anything out of it, at least during one run of the compiler, that means that you're holding on to a lot of stuff that's garbage, at least if you're just running the compiler once. But if you're running several times, then you can reuse some of the values from the last time. So it's actually, at least from a tooling perspective, not always garbage. You can and you want to also perform garbage collection on that cache, because if you're making a lot of changes to the source code, you'll have a lot of queries in the cache. If you never remove anything, you'll have a space leak. But so what you do is you keep track of what's been fetched during one run of the compiler, and then from the previous run of the compiler, you can remove everything that wasn't fetched in the current one. That makes sense. So you have garbage collection there.
And I really like what you're saying at the end, that this will provide a key to scalability because you can parallelize the queries as much as you want. So I'm curious, have you gotten the chance to try it on some large scale code base where was the reality of the performance what you were expecting?
Not really. So there aren't a lot of programs written in Sixten, my programming language, unfortunately. I have, however, tried it on like some generated programs of a lot of nonsense, and it seems to work quite well, at least. It does get a bit slower with a lot of modules, but works quite well, I'd say.
And will this work for any programming language out there, or it's just for functional programming languages?
I think it would work for any language. It might be more or less work to write the compiler in this style or rewrite the compiler in this style, because it's a little bit of another way of thinking than you might be used to writing compilers.
Right. Last question from my side, and I am told it is a provocative question for Haskell developers. Do you think Haskell makes it clearer for engineers to express themselves, or just harder for others to understand
them? Maybe both. I mean, if you don't know Haskell, it's going to be hard to read it, of course. But I think it's a language that allows you, if you know it, to express ideas very precisely, sort of without weird corner cases that you might have in other languages. In that sense, you can express yourself very clearly, I think.
Excellent. Olle, thank you very much for your talk. Thank you for being with us today.
Thank you.
Now